Okay, so definite integrals is kind of the central topic of these the last exam and the final here. And these have to do with finding the area under the graph of a variety of curves. So the definition of a definite integral is given by the first part of the Fundamental Theorem of Calculus, which is if you see this, the integral sign, from a to b of some function. So what that means is that you're taking the integral of this function from a to b. So these a and b are just two x values. You're going from a to b. What this equals is capital F of b minus capital F of a, where remember capital F represents the antiderivative of lowercase f. So you take the antiderivative of your function, evaluated at b, subtract it from what it is evaluated at a, and that's your definite integral. So this has a variety of different meanings and a variety of different uses in your class. So this gives you the area under the curve. However, it doesn't exactly give you the area under the curve. For example, if you had something that looked like this, some trigonometric function maybe, and you did the integral from 0 to whatever this value is right here, and you wanted to see what would happen. The definite integral, assume that these two sections right here have the exact same shape and area. The definite integral from 0 to, let's say, c here, the definite integral there would be 0 because all of this cancels out with all of this and essentially it nets you 0. So the definite integral by itself gives you the net area, not the total area. So let's think about what that would mean if you wanted to get this total area. Well, if you knew what the graph looked like ahead of time, you could just do the definite integral from here to here instead. So let's call this c over 2 since it would be in the middle. And then just whatever you got there, double it. If you didn't know, however, what you need to do is you need to find where this function crosses 0. So what you would want to do is you want to say f of x equals 0, figure out where those are, and then you'd have to do this. Integral from, let's say, c, we found that it was c over 2. You do the integral from 0 to c over 2 of f of x, and take the absolute value of it. And then you do the integral from c over 2 to c of f of x, and take the absolute value of it. So, like I said, in this case, since we're looking at the graph, it would be a lot easier to determine. But if you didn't know what this graph looked like at all, and maybe it's a really complex function, all you'd have to do is set your function equal to 0, and if there are multiple points, you'd have to split it up into multiple intervals. So, however many zeros you have, you want to start at the beginning and go to the next 0, and then go from that 0 to the next 0, and on until the end. And each one of these sections, you want to take the absolute value of. So remember that we can do this because there's a rule for definite integrals that if you have the integral from a to b of f of x, that's the same thing as if you split it up at a common element. So if you went from a to c, and then from c to b. So this, if you stop anywhere in between a and b and add them together, you get the same as if you did the entire thing. However, this is different because we're doing absolute value, because we want the actual total area, and we don't want the parts under the axis to count as negative if you want the total area. So there's a couple other things that you can do with definite integrals, so let's go over some of those basic rules. Another one is that if you switch the bounds of integration, so we have our regular a to b, if you switch it to b to a, in essence going backwards along the integral, you have to put a negative sign here. So this is always the opposite. If you go backwards along the line, you always get the negative of what you would have got if you had gone forward. And like I said here, you can split it up into multiple sections. use the fundamental theorem of calculus to evaluate that. If you want the total area, you have to set your function equal to 0 and use absolute value around each section. So this is really useful in problems where you're doing total distance, if you're given a velocity function, if you need the total area of a curve like this, you have to use a definite integral for all of that stuff. So the definite integral is going to comprise a lot of the problems that you have. And keep in mind, this always should result in a number because you're plugging in a number to the antiderivative every time you end up evaluating it.